It's my pleasure to introduce Christian, who will talk about urgap, Unified Resource Governance and Data Provenance. This is the title which was announced. Yeah, Christian is by training a biochemist. He did a PhD in Freiburg, um, 2001, and then has spent postdoc periods in France and at the City College in New York before he moved to Münster as a postdoc and a group leader. I think at that time still working mostly on omics and proteomics. And since 2017, he is at GSK here in Heidelberg, on the EMBL campus. So for people who might not know that Cellzome is also linked to GSK, although I'm not a specialist of pharma companies, I have to say. But they have there's actually quite some activities around EMBL from there. And there he was initially a group leader on computational mass spectrometry, and is since 2022 the director for data streams and operations. And yeah, we had an already scheduled a meeting for 2 weeks ago, and we met. Actually, Christian is also a lecturer at the University of Heidelberg, so he's also interested into corporations both locally in Heidelberg, but also since this is a virtual series across Germany, and so he's very into open source. I learned from the coffee we had instead of the lecture. And yeah, we're looking forward to your talk and to hear more about the tools. And I think there are many applications around topics like GHGA, which are linked to the topic of your talk. So, Christian.
Excellent. Thank you for that very nice introduction. Let me do this here. Share, no, not window. It worked so well before, right? So share screen. Yes, entire screen. Okay, good. Okay, so excellent. Thank you for the introduction again. Thank you for giving me the opportunity to show what we have done. We, that is collaboration. Yes, I'm at University of Heidelberg, but also at the University of Bern and Rochester Institute of Technology, and of course GSK. So we built urgap. We built urgap because, and as the title about challenges and solution, building modern industrialized data pipelines, right? So that's what we do in GSK. We build industrial pipelines. And I'm going to talk a bit about our journey. But what happened here? I cannot move forward.
The sharing stopped.
Yeah. Sharing stopped. Oh no.
Need to reshare.
Okay. Okay, I share again. Share screen. Share screen. Share screen. So,
yeah.
As Jan already said, I started studying in Freiburg, moved to France, and then to New York and Münster. And you can see my subject moved from math to biochemistry and more into bioinformatics. And then after habilitation, I joined Cellzome GSK at the EMBL campus. And you can see already that was much more bioinformatics, more engineering, and all that plant stuff that I did before I left behind. I umhabilitiert at that point at the COS, still having scientific collaborations with the Leidl group around tRNA modifications and influences on translation. And also with the Schulze group at Rochester Institute of Technology around computational mass spectrometry nachher. And after a few years, it became clear in GSK that the engineering that I brought and that I established at Cellzome, they were actually really interested in moving it out and making it available to bigger GSK audience. So I was promoted director data engineering. We do now a lot cloud software data. It's all engineering in a way now at GSK Heidelberg. And as it happened to be, also this new faculty was founded. So I umhabilitiert again into this faculty now. So everything in one picture, if you like. Currently, my team at GSK, we are 32 data engineers. You can see we have 10 full-time employees in orange around Germany and the US and Canada, and then complementary workers from all over the place, all the world, Argentina, Mauritius, Poland, UK, India. And you can imagine with a stuff like that, there is a lot of things that we have to do, a lot of things. And we can, I can separate our work streams, if you like, in three main fields. So, ooh, can I use actually my mouse pointer here? Laser pointer, nice. So when we have data engineering, our data generating lab equipment, you can imagine the data needs to be surfaced into the cloud. And in GSK, we work on GCP and Azure. And on top of those cloud platforms, we build Code Orange, and not we, but the company, build Code Orange and Onyx, which are platforms on top of the cloud. You can imagine that lots of things about security, governance, and all of it have to be regulated on a platform level. So it's not wild, wild west. And at the end, these platforms surface the data for reuse, AI/ML, insights, decision-making, and so on and so forth. Now you can also imagine some of the data that is generated from lab equipments, they are not ready to be surfaced because they're not in an analysis-ready state. And at that point, what we do, we create analytical pipelines. And they run, as you can see, on Azure and GCP, depending on where we surface the data. And they run on Kubernetes because we need to stay as cloud native as possible. We need to be able to move one application from one side to the other, depending on the demand, depending on novel technologies. And I'm going to talk about analytical pipelines today, only about that one part and what it means. So it's, as I said, from unstructured data, as you know a lot of, I guess, to structured data, Parquet into data, Delta lakes, and so on and so forth. When we did this, and over the years, our aim was always, we had a certain requirement, right? We could not be locked in, as you understand, we have two clouds. We cannot be locked into a cloud, so no cloud-specific technologies. Think, for example, Azure Data Factory wouldn't work on GCP, so we can't use it in that sense. So we want to be not locked in, not in cloud, not in platform, and not in orchestration. And that doesn't mean we don't want to make a call. It simply means we want to use all of them transiently. The second requirement, quite importantly, was no compute should be done ever twice. Because as you can imagine, we have lots of data pipelines, lots of data. Reprocessing costs a lot of money. So it should only be done if it's explicitly wanted. Furthermore, a requirement was file abstraction. So we wanted to have, to be able to address files in, again, cloud storage-based agnostic fashion. That means it shouldn't matter if the data sits on GCP or Azure, we should always be able to tell these are the same files. So file identity, file abstraction is key to anything we do. And with these two, the last 2 points, actually, they come down to the same thing. That is simply the moment you're not locked in, the moment you have designed your analytical pipelines in a very agile fashion, you are able to implement novel bioinformatics tools rapidly in the pipelines, but also on the engineering side, right? When Netflix releases the new orchestration tool, as a data engineering team of that size, we need to be able to test this. Is this helping us? Are we faster? Is it more robust and things? So being able to stay cutting edge requires no lock-in, requires all these requirements to be set up. So how did we get there? We built urgap, which is an encapsulation layer around the tool itself. So then if we run Nextflow, DNA Nexus, Prefect, Dataflow, whatever, we stay independent of that. And also around the scaling platform and also around of the platform itself. So how did we get there? And I want to walk you through. So let's go back and I show you the example or the challenges we faced based on a ribosome profiling data analysis pipeline. Obviously, all these challenges have not being discovered on this pipeline, but I use this as an example. So this is a simple ribosome profiling pipeline done by Tristan Ranf in my team. He's a PhD student right now in collaboration with the Light Lab. And here we look at how translation speeds change due to altered DNA modification. So we're interested at this blue box in the bottom, the codon metrics. That's what we're interested in. The dark blue ones are actual outputs that we look at, so 2 QC files and the codon metrics. The black boxes are the input files that we use. The light blue boxes are intermediate data products, if you like, and red ones are the processes. So what happens is in the beginning, we have new reads, a new experiment. It goes through some pre-processing as well. We have ribosome RNA, and we use Bowtie to extract those ribosome RNA reads out of it. Then we have unaligned reads. We use star in a human genome. We use a star indexer. We align those, again, some pre-processing, and at the end we throw it into its riboprofiler. But it's just it's a placeholder. Tristan works on a name, and here you have faster GTF and experimental design flowing in to produce codometrics. Okay, so based on that pipeline, let's go through the challenges that we had. Ambiguity regarding the identity of files, as I said. When does that happen? Maybe when does that happen? So an easy example is if you have if you move your experimental files, these FASTQ files are now moved from GCP to Azure. And when you move them to Azure, then how do you know these are the same? How do you know the file was not corrupted? Or in a different scenario, imagine you get an email from your PhD student, it gives you a CSV file. How do you know it's the same CSV file that she is looking at? So identity of files, independent of storage background, is really important for anything we do. And how did we tackle that? Well, it was already solved once, and that was for books. So we just piggybacked on the same idea. So we created the urgap canonical file signature, which is inspired by the ISBN. So the ISBN, everybody knows, the code that tells you this is the identity of the book. It doesn't tell you where the book is. You can go on a website and check which store has it, which library has it, but it doesn't give you the book. So we adapted the same pattern, and we defined files by URI strings. So it has a schema. The schema tells you how do you talk to the storage backend. It has a location. Where is the storage backend? And then we use that hashtag in URIs, in the standard URI format, that defines a fragment. So behind the fragment, this is what we call, this is the object name. It's independent of location. So this is how we separate these two things. Now, object name might not be unique, where you can imagine you have whole namespaces behind with slashes and stuff, although they don't exist in buckets, but you can imagine this is like the object name. So to make it then unique, what we add is an @ and the MD5. So it's the hash for the content of the file. These hash algorithms can be exchanged in the implementation if you like. We use MD5 for now to define UCFS. What happens behind the scenes with this UCFS is also we coupled it with the credential manager. So to give you the whole picture, how we define files is you define it with a URI, that is this here, has a host, has a container name and an object name. And then we create a U file. So our Python object for files. Now, based on that URI, we have a schema and host, and with that, it connects to the internal credential manager. And the credential manager can be configured to use Azure Key Vault, environment variables, or GCP secret store to extract for this host and that location, user and password. So you have access to these remote buckets as well. Now, the file itself exists in two states. So some of the states you can access remotely if the backend supports it, via tags, for example. That is MD5. So you can check on remote what MD5 it has. The moment you access the attribute.path, the file is actually downloaded onto Scratch disk, where you process once, so where you initialized actually U file. So that means no matter where you initialize your U file, as long as you have everything set up, the file is downloaded to the point. Your container, for example, or your VM. So coming back to the question, the beginning question, how are those files the same? Now we have the treat file here on GCP, here the treat file on Azure, and I also have it locally. Programmatically, what we do is simply, I initialize urgap file with this location, with this URI string and that URI string, and when I print out the UCFSs, I get the file name, so the object name, plus its MD5. At this point, I know all three are the same. So what can we do with this now that we have identity separated from location? This is the essential first step to build up a data mesh, if you like, because now it doesn't matter where the file is. You can even go further and say, hey, do we actually need to know where the file is, as long as we have the UCFS? And this is the second challenge we faced. This is still not in production. This is a beta stage, but we can, in principle now, provide data from the closest storage and also from the compliant storage. So what does that mean? As a scientist, I can say, I need this human genome. And I ask a microservice or an agent or whatever, I need this file. Now, where are you located? He might ask, or where do you want to run your pipeline? Two different things, right? And then let's say the user says, I'm in Heidelberg. The agent will look, okay, in my internal, this object name or this UCFS, where is it stored? It checks. In Azure, there is no storage, no data center in Azure close to Heidelberg. Equally, not close to in GCP, also in Google. There's no data center close to Heidelberg. But the Denby has a data center right in Heidelberg. So it replies with a hi box link. And I'm sure this is not the right thing for Denby, but this is in principle how it works. So now we can actually start writing data pipelines that don't need to know the location because it's handled under the hood. The location is filled up by querying an agent or a microservice, if you like. So object names can be enough as long as you don't have the same names, right? Migrate CSV might have lots of collisions inside the data mesh, but if you combine it with its MD5, so it's UCFS, if you like, it becomes unique. I'm rushing, hopefully not too fast. Hold me back. So, challenge number 3, never run any compute twice, except when explicitly forced. Now, this sounds maybe not so intuitive. Why would you need that? You don't need that really, right? So let me explain to you why we think we needed that and why it made our lives so much easier. So imagine you write your NGS pipeline, coming back to our ribosome profiling example. We could include this indexing step, so human genome here, create the index, have the reference index, and then off you go. We can include that step in every pipeline, or we could actually not include that in a pipeline and just start with the reference index. Two different ways that you can do it. What are the advantages? The first one is, well, you have the highest data consistency. The moment you trigger your pipeline, you can be very sure that this is the original FASTA that you use. It's not something somewhere. This is the FASTA. It will create an index. So it is creating a significant compute overhead. On the other hand, if you plug it out and you say, like, I want to use the new version of it, you don't have to change your pipeline. You just throw in the new genome, it'll work. Excellent. Well, I don't need that. You can say, I don't need that compute overhead. I can just start with the reference index. Well, yes, you don't waste compute without smart rerun logic, yes, but it requires tribal knowledge. When was that created? What was the parent? Is that well documented? Where is it documented? And you will also require a second pipeline that will create your index. So the moment somebody says, say, I want now a new genome, then you will have to trigger the other pipeline that creates that index, and then store that somewhere where people can look it up and say, like, if you want to use that new genome, you need to use that reference. So it requires lots of tribal knowledge. And that's why we wanted to have a smart way to run that all the time. We include it all the time because then it'll become explicit. The pipeline is very explicit. What would be great if that is not limited to that pipeline. So if Tristan is running ribosome profiling on that human genome with a star index, and somebody else runs bulk RNA, they both should profit from the fact that this has been done in the past. So how do we do that? The solution came with data provenance as code. That's what we do. And it's simple as you cannot compute output file. You cannot define output file names. You have to compute them. That's key. And that comes like a paradigm shift, right? Because it'll change how you look at data. First, what does it mean, computed output names? What we do is we compute the output names based on the parameters, and there's a wee star here. And the star means, well, only parameters that change the output. Like if you flag that CPU will not change the output of this processing step, this will be taken into account. Then it is based on the input file UCFS, because now we are independent of the storage backend. We have well-defined ISBN-like identifiers for all the files and the processing step. And what happens then is the output files are computed based on the first block will be what's the processing node, so bow tie, for example. Then you'll have the parameters, the MD5 of all the parameters that are used to produce that file, and then the MD5 of the sorted output files. So next time somebody comes and like, I want to run this again, but I change the parameters, we will have a new hash. Data will not be overwritten. Everything will be kept. So we have a nice trace. What it also means is within this signature here, you actually have information of its lineage, if you like. It has a parent fingerprint. You cannot reverse it. You cannot find out the lineage from these hashes, obviously. But we also store the data lineage inside the tags of the files. But that's a different story. What is important is this is a fingerprint that you can compare against. So if you get a CSV file by email, you'll be able to know if it's exactly the same as your PhD student is working on, for example. So files are never overwritten. Everything is very, very well defined in terms of files. And when I said this changes the way you look at data, well, the fact that you had in your, let's say on your storage base, you have folders that encode, if you like, metadata, right? Experiment 4, repetition 5, and all of that, that's gone. You cannot go into the folder and find your file. It's all hashed. Comes like a little shock, but in a way you can think of in your iTunes library, it looks exactly the same. The files where they sit is not important. You want to have an interface that you say, I need more heavy metal music, and it'll find all the songs independent of where they sit. So you can have different groupings and all of this. And accessing those files programmatically also helps to filter by metadata, much easier than grouping them in another folder and only looking at this. Different story though. So having that in place now, what we can really do is if first scientist, she runs a pipeline, calculates the index, runs her NGS, bulk NGS pipeline with that, this referenced index will have a pre-computed name and is available to all scientists if you have a data mesh or if it sits on the same data backend storage. So then next time Tristan comes and runs his ribosome profiling, this will be skipped because it already exists. So it's cross pipelines, if you like, as long as you work with the storage backend properly or have it set up in a mesh, as I said in the beginning. So advantage of it is really everything becomes explicit. There's no tribal knowledge. Who has created that index? Where is that index? Or you need to find that person because he will create the new index of the file that doesn't exist. This is all gone. You can always include the indexing step. Next challenge. New data storages have to be covered. What is that? You probably don't come across that, but in the industry, we have that a lot. Example. So we have these FASTQ files, and now the supplier, people that measure it say, actually, we have changed our workflow. You need to pick up your files from the Azure Samba share. Okay, easy. Or from our proprietary storage, which is behind an API. You need to include the API. Now what you can do is, well, we can write a script that pulls the file and puts it into our bucket so we can start processing it. Complicated, right? Because not all pipelines will have access to that interface, if you like. So how can we make that happen? As you can imagine, the solution we have already put in place because we talk to files in URIs and the URI, the schema defines how you talk to the storage backend. So in here, we have generalized data input output that sits behind the U file, if you like. And depending on the schema, it'll use another class to talk to the backend. So we can actually implement OMIC, which is a third-party provider for flow cytometry data. We can enable an OMIC interface, and all of a sudden our pipelines can read from OMIC as if it would be sitting on local, on Azure. It becomes all transient because for that process here, if I do ufile.path and it downloads it, it doesn't matter where it downloads it from. Some interfaces support uploads, some not, like HTTPS doesn't, obviously. But for example, GitHub, if we upload, we automatically create pull requests. So we can store version data also on GitHub, if you like. And as I said, this is all hooked up to the secret management. So that was easy, right? Because we have it already abstracted. There's an interface for files to use. Next challenge. Fifth, I swear there are only 6 challenges. So fifth challenge, like zero-touch deployment of novel and updated processing steps. In my team, there are many scientists, so we know the pain of it. But now we're data engineers. We only want to enable the automatic or the smooth work of scientists, if you like, in that sense. So what is behind zero-touch deployment? You know, you have a pipeline and then there's a new bow tie coming out. You'd love to test it. You love to test it, exchange it into the pipeline and just run with it in UAT, let's say, user acceptance environment. So we have like different environments. Production we don't test, but like to test, right? To play around. And we want to compare the results. Well, that we don't have to check anymore, right? This is data provenance as code. You change the working node, it'll automatically create new data packages. You can compare them, no problem. But how do we do zero-touch deployments? How does that work? So I have a new version of some product. Yeah, for example, Tristan has a new version of his. How do we get it automatically spin up into the pipeline and be able to trigger without anybody doing anything? That was a challenge, and we solved it by encapsulating before we deploy. So we split this DevOps, if you like, into two elements. One is the scientific DevOps. We teach a scientist, and some know that already, right? It's just giving a hand. How do you do it if you don't know how to do it? You, in a sense of scientists in GSK. And we help them. You have your SME code that is special meta expert. So a new clustering algorithm, a new analysis of something rather. You have that code. It runs in R. We show them this is how you build your container. Okay. In your container, you need to provide integration tests. We need to see that your container does exactly what you want it to do. Input, output, everything's in there. The moment this container is built, the tests passed, container is built, container is shipped, what we do is then we look at this container registry, and then we do the tech DevOps part. We look at the container. As soon as it's there, we pull the container and we install urgap in it. What happens with it is we will expose the scientist code as microservice in the container. And then, because our pipelines with different orchestration tools, if you like, as long as they support containers, they run in UAT, not production. They run latest. And if they run latest, Kubernetes will realize this is a new container that was created and pull it automatically into the environment. So at that point, data engineering doesn't touch that environment anymore. The scientist upgrades, everything's green. As long as the checkboxes are green, it'll flow automatically into UAT. So new versions can very easily be deployed. Makes it very powerful, and scientists are very happy about that, I can tell you. Last challenge. Fourth switch of orchestration tool. Right. You probably don't know any of this, and you live in a happy world where you don't have to switch your orchestration tool. We are not so happy. So in 2024, we developed pipelines on GCP using Dataflow. Dataflow, there's an open source version called Beam and Flink. So the moment we had to move the pipeline, and not move like migrate, but spawn the same pipeline for clinical data into Azure. So in GSK, that's split. Clinical data runs on Azure because it's validated environment. Research data runs on GCP, not validated. So we bring in the pipeline, we use the open source version of it, run on Azure, problem solved. Turn out, Flink open source version 1.17 memory leak. Container died in Kubernetes after X runs, then respawned thanks to Kubernetes, but couldn't find the orchestration layer again. So it was really a showstopper. We had to stop everything. Now what do? We thought, let's look at the market, what is there? And we found Prefect. If you don't know Prefect, have a look. It's really interesting orchestration tool. It's a new kid on the block, not so new anymore. Actually, it's quite established, I would say. And we migrated the complex data pipeline in 5 days. 5 days. And that was only possible because did we have to explain Prefect where the secrets are? No. Did we have to explain how to read from MyLab data or make GitHub Azure? No, nothing. The whole pipeline actually turns out to be, this is just passing text strings. So our pipeline is, these are the input files, these are the text streams, these are the processes, this is the config, and it goes on by itself. Even the process that were already run on this, because of the smart rerun logic, could be skipped because the data product still looked the same. So that is our success story right there. And I can only show you, this is an example how we stay agile, how we can figure out this is the new kid on the block. This is something new we want to try with all our analytical pipelines, with all the nodes, and we can easily do it. We can easily migrate. So where does it bring me now? What is the future of data engineering, I think? The future of data engineering in that current hype, agentic AI, there is no data engineering anymore, I think. Soon, everything will be actually a prompt, right? And if you think about it, in the material and methods in your paper, you write already the prompt, right? You said this file was analyzed this with the parameter of blah, 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 blah. So that's already a prompt. All you need to know now or have to have is an agent that can interpret your prompt and then call the right tools in the right order. That's the ultimate. And because the agent itself is just an orchestration tool, if you like, then our success story that I just told you about, changing it in 5 days, actually also applies to agents. So yes, we could turn a pipeline within a few, not days, but with a few, with little resources actually, and make it agentic. So now we have something that looks like this. Hey, I have CSV files that sit on MyLab data. And as I said, MyLab data is this proprietary GSK data capturing tool, if you like. It has an equipment ID, a task ID, and these CSV files, I like to filter them using this pandas query. And when you have done that, then upload the results to the GCP project. So upload them to cloud, actually, to another cloud, into this project and this bucket. And when you're done with that, run a Venn diagram. I'd like to have a Venn diagram with plate name and subject ID for ID and value columns. So a Venn diagram that shows you on your CSVs, how are the patients distributed, if you like. And at the end, create a zip file. Zip them together so I can download them later. Okay, and this is what I show you now as a demo. Okay, this is what we did. And on the left, you see a bit the plan that you can imagine. So I asked the user asked this to the machine, asked for a plan. The plan is generated, and then we have human in the loop. And the black boxes are the MCP tool calls, if you like, or agents. They can be split in agents, if you like. They are fed with files here from MyLab data or with light blue boxes. These are all LLM elements, if you like. The large language model will provide parameters or format parameters, if you like. So this is a live demo, if that works. Let's see. Yes. So I use Chainlit to have that demo, turn it into white so it's easier to read. And I will, oh, no, I cannot control it. Wait, I can also do it here. Okay, this is better. So this is exactly. So as I said, I use Chainlit. This is like an environment for LLMs, local LLMs. We use Gwen 30 billion. That's a local LLM. It's all cheap, and it found 7 tools. And this is the bucket where we want to land. I refresh the bucket, and you see it's empty. Okay. Now we hack in the prompt. You know the prompt already, right? I read it to you. I'm not so good voicing it over, so sorry for some of the breaks, but it's in principle exactly the same prompt as I read out before with subject value and so on. We send the message, and this is in real time. So this is a relatively fast LLM. It's a small one, and it builds up a plan. Okay. And if you look at the plan, the first step actually is, yes, use MyLab data to grab the storage pattern, right? Because if we want to list files in MyLab data, we need to provide from the information of the user that gave us the task ID and equipment ID, we need to generate that urgap, if you like, the URI string, how to list these, right? And in the second step, yes, we can then list the container items. And you see already here, it formats in the result of step 1. So the LLM creates actually a whole plan what to do. And it also does here, the light blue box, it remembers, hey, he wanted to list the CSV files. So I can pass in the regex since the tool has a keyword argument regex pattern string. The LLM automatically formats the file has to end with CSV because I'm only interested in CSV. Nice. Then after listing the files, it generates another URI string because I need to upload it to GCP. So it says, hey, create a GCP urgap storage pattern. This is step 3. Nice. And 4 then runs filter CSV based on the U files from 2, and it should push the results onto 3. And also formats the pandas query into the right output already for me. Excellent. Now here comes the thing. If you if you use LLMs to create plans, they need to be creative at one point, so they make mistakes. And here you see step 5 is actually not my 5. It calls the same tool as 3 again. Okay, I can live with that, no problem. And we need to add validation agents in the future, but that's something we're working on currently. So step 5 here is then step 6. It says create a Venn diagram. The files are from step 4, formats the parameters correctly, and stores it now into 5, which is the same as 3. And at the end, we zip it, compress those files. Result is 4 plus 6, and then put it to 3, right? So you see 3 and 5 are exchangeable. And then below, you see it's human in the loop. So it'll ask me for each step, do you want to proceed? So here is step 1 of 7. Use the pattern, generate the connection string, if you like. It proceeds, executes the tool, writes the JSON, shows me this is what I'm gonna do. I execute the tool, and this is the result then, right? Now I can list the tool items, so it can connect to my lab data, and it starts listing the tools, listing the CSV files. It formatted all the parameters in there, and here's the output. Now, yes, 3 CSVs. Now, please note, right, the agent itself did not know anything about how to talk to MyLab data, where to get the passwords, all of that. That's all urgap sitting below as an MCP server connected to the agent. So again, accelerating our work because we just pass text strings here, and that is perfectly valid for an LLM. So we have 3 CSVs now. Excellent. It calculates then the next step, or not calculates, it calls a tool that generates the storage pattern. Here, GCP. Proceed. Yes. Makes an MCP call, says these are the parameters I know. What is the storage base UI for it? And you see the schema is GCS libcloud. So that's a way how we talk to GCS, one of the many ways we talk to. This is an old one. Formats the files in now for filter. So the 3 that it identified before as, again, URI strings. Formats the Panda query in here and calls the tool filter CSV. And then we have as an output a long string. And you see also some of the information that is passed through and available as tags. But if you refresh now the bucket, you'll see the CSV file has been uploaded. Now we go on and say, okay, now create that pattern again, that storage pattern if you really need to. You don't have to, but again, this is something the validation agent comes in. It generated the same, thank God. And then we run the Venn diagram. Creates a Venn diagram, formats all the files in that we had before, so the filtered CSV file and so on, and runs the tool again. The advantage of CSV create a Venn diagram is that the output is an SVG, and SVG can be natively viewed on GCP. So if we go in here now, refresh again. Yes. Then we have a Venn diagram. And if you scroll down, you will actually see the Venn diagram. Nice. So between plate and 1 and 3, you have 16 patients overlap, and plate 2 has only 4 patients, no overlap. Right. And then we call compress. And you can imagine, yes, the compress nodes gets 2 U files, that is the filtered CSV and the Venn diagram together as pictured on the left on that schema, and executes the tool. The agent executes the tool. It's the last step, exactly, compress. And when it's done, we'll have a zip file in the bucket that we can download. Right, also gives you a nice summary, what happened exactly. You can access the final file over there if you like, or you go to your bucket. Compress zip file. which you can download. Yes. And the file has the CSV in it and the SVG. The SVG is the Venn diagram, and also tag files. And tag files is something urgap does for all storage backends that do not support tagging. So we store the tags into tag files, MD5s, metadata, data lineage, and so on and so forth. So exactly. So this is the demo, and this only works because we have encapsulated the process. And I hope I made you now interested in encapsulating your process and moving away from standard folder structures to hash-based signatures. We have done this now. We have some data manipulation, visualization, some EDA, exploratory data analysis tools we have in there. NGS, some, yes. Proteomics, metabolomics we had in the past, but that sort of is not supported anymore, but it's coming. Stefan is working heavily on it. The Beacon platform is supported in Interdoc. And you can see we have also different metadata storages I did not talk about too much. So in summary, I hope I made you understand why we did this and how important it was for us. And that now, as an orchestration tool, we have also AI here. We can expose all the tools via AI. I showed you that the urgap container, when we do it, has standard interfaces to many cloud things. Yeah, I did not talk about metadata capturing. I did not talk about the lineage, if you like. We record the lineage as well. And I did not talk about open telemetry. So all these containers, as you can imagine, they expose all the logs, all the things that happen in there as open telemetry. So we can capture these via of many different pipelines. So doing it in this container is not telling you which orchestration tool you can use or not, or maybe it limits you the choice, but it gives you the freedom to jump. And that's important for us, being really flexible at that point. So incorporate the logic in one place and use it everywhere. So finally, yes, the outro here. Reach out if you like. These are the contacts. If you want to have early access to the source code, become part of the community. So this is not Fufezan Lab or anything like that. This will be the urgap community. So you can join it, become major contributors. It's private right now because we need to delete all the CellZome GSK elements of it. And if you like, I'm at the Emble campus twice a week. So ping me for coffee or so. Or if you like to have the urgap white paper, we have written it already. And here are the main developers. And with that, I stop and I'm open for questions.